Hey everyone, and welcome. I am absolutely thrilled to guide you through this explainer today, where we're going to look at the very foundation of how we process data. Seriously, if you've ever found yourself wondering how algorithms actually make decisions, or how we can mathematically measure the sheer amount of data flowing through our world every second, you are in the exact right place. We're going to explore a structured, brilliant framework for quantifying information. It's this wild journey that takes us from the very basic human emotion of surprise all the way to complex machine learning models. Here is our roadmap for today. 1. The degree of surprise. 2. Quantifying uncertainty with entropy. 3. Comparing distributions using KL divergence. 4. Mutual information. And finally, 5. How machines actually learn. Okay, let's dive right into Section 1, the degree of surprise and measuring information. This is absolutely foundational for how we need to think about data. So, how do you mathematically measure surprise? I mean, it sounds almost like a paradox, right? Surprise is an emotion. It's that feeling you get when a massive plot twist happens in a movie. But in the world of statistics and data, it is a highly rigorous, perfectly measurable metric. And to understand how on earth we compute an emotion, we kind of have to look back to the origins of a very specific mathematical framework. That framework is information theory. It was introduced by Claude Shannon in a groundbreaking 1948 paper while he was working at the AT&T Bell Telephone Laboratories. Information theory literally gave us the tools to quantify, store, and communicate information. I mean, Shannon is the guy who introduced the word bit to describe a stream of ones and zeros, completely paving the way for the entire modern communications revolution. But to actually make this work, Shannon first needed a way to define what information inherently is. And here is the really crucial part. Think of it like a heuristic. The amount of information we receive is directly proportional to our degree of surprise. Just think about it for a second. If I tell you that an event you were 100% certain was going to happen just happened, you've received strictly zero information. Your knowledge of the world hasn't changed at all. But if I tell you a highly improbable event just occurred, your degree of surprise is massive. Therefore, you've just received a huge amount of information. Basically, low probability equals high information content. Moving on to Section 2. Quantifying uncertainty with entropy. Now that we've established that surprise basically equals information, how do we calculate the average amount of this surprise across a whole system? Well, we use entropy. There is actually a pretty great story behind this name. When Claude Shannon was first formulating this concept, the brilliant mathematician John von Neumann supposedly advised him to use the term entropy, which, was already a thing in thermodynamics. Why? Because, as von Neumann joked, nobody knows what entropy really is, so in any discussion you will always have an advantage. It's a fantastic piece of scientific humor for sure. But mathematically speaking, entropy in information theory is just the average amount of information needed to specify the state of a random variable. Let's take the absolute simplest example you can think of, a coin toss. If a coin is completely fair, it represents total, pure uncertainty. You have absolutely no idea if it'll be heads or tails. In information theory, the maximum entropy of a fair coin flip is exactly 1 bit. It requires exactly one binary digit, a 1 or a 0, to describe its completely uncertain outcome. But what if the coin is biased? Say it lands on heads 99% of the time. Suddenly, the outcome is highly predictable. There's very little surprise, which means the entropy drops down close to 0. And this brilliantly illustrates that exact concept, just zoomed out across wider datasets. Take a narrow distribution where the data is highly clustered. Because it's predictable, the entropy, which we denote as H, is a lower 1.77. But contrast that with a wider, more uniform distribution. Since any of those states is roughly equally likely, the uncertainty, and therefore your potential for surprise, is so much higher, giving us an entropy of 3.09. Simply put, a uniform distribution inherently holds way higher entropy than a narrow one. We actually see this in action all the time with data compression. If you have a variable with 8 equally likely states, communicating its identity is always going to take 3 bits of data. But if the distribution is non-uniform, let's say one state happens 50% of the time and all the others are super rare, the entropy drops down to just 2 bits. Why? Because a non-uniform distribution lets us use clever, much shorter codes for those highly probable events, and we just save the longer codes for the rare ones. Less uncertainty means less data is required to transmit the message. This is literally the math that allows your streaming video and zip files to work every day. Section 3. Comparing distributions with KL divergence. So, what happens when we don't actually know the true distribution of our data, and we try to use a shortcut or an approximation to describe the system? Well, when we approximate an unknown true distribution, let's call it P, by modeling it with a completely different distribution Q, we naturally lose efficiency. The Kullback-Leibler, or KL divergence, measures the dissimilarity between these two distributions. You can basically think of KL divergence as the literal penalty you have to pay. It's the average amount of additional information, or extra bits, you require to specify a value simply because you used an approximation instead of the absolute truth. The less your model matches reality, the higher that KL divergence penalty is going to be. Now, here is a truly fascinating quirk. KL divergence is strictly asymmetrical. The penalty for substituting reality with an approximation is not mathematically reversible. The distance from P to Q is absolutely not the same as the distance from Q to P. This tells us that measuring the divergence between a complex reality and a simple model behaves fundamentally differently depending on which direction you are looking from. It's a one-way street. Section 4, Mutual Information and Variable Relationships. Let's see how this all builds into relationships between different data sets. So the main takeaway here is that mutual information measures the statistical relationship between two variables. If you have two variables, x and y, their mutual information is quite simply the reduction in your uncertainty about x purely because someone told you the value of y. If knowing y completely eliminates your surprise about x, they have high mutual information. But if knowing y tells you absolutely nothing about x, they are completely independent and their mutual information is exactly zero. Which brings us to Section 5, How Machines Actually Learn. We have built an incredible theoretical scaffolding today, from human surprise to entropy to divergence to mutual information. Now we're going to tie the entire narrative together by seeing how these abstract equations are the literal, foundational building blocks of machine learning. Let's look at the classic ID3 decision tree algorithm. Imagine a machine learning model trying to predict whether someone will play tennis on a given day. We feed the algorithm 14 days of historical data. 9 days they played, 5 days they didn't. Because it's a mixed bag of yes and no, our starting entropy, our initial uncertainty, is 0.940. The algorithm's entire goal in life is to reduce this entropy to zero. To do that, it tests an attribute, like the wind, and asks, if I split the data into days with weak wind and strong wind, how much does my uncertainty actually drop? And here is where we literally see the math in action. By calculating the entropy of the days with weak wind and the days with strong wind, the algorithm finds its information gain. Just by knowing the wind condition, the algorithm reduces the starting entropy by exactly 0.048 bits. A machine learning model will systematically test every single attribute it has, humidity, temperature, wind, and it will always choose to split its decision tree on the attribute that gives it the highest mathematical information gain. It is quite literally hunting for the variable that destroys the most uncertainty. Which leaves us with this one final thought. We started with human surprise and ended with an algorithm systematically devouring uncertainty, just one bit at a time. Every model, every classification, every learning algorithm out there is just a relentless drive to minimize entropy. So if learning is just the continuous reduction of uncertainty, it forces us to ask, is the universe, at its very core, just a massive sequence of computed bits waiting to be decoded? I'll let you ponder that one. Thank you so much for joining me on this explainer, and keep questioning the data around you.